When Kyongyong Cho arrives to teach his advanced machine learning class at New York University, he's stepping into one of the most elite academic environments in the world. Cho is an AI pioneer who helped design the architecture behind modern language models, and his students are senior computer science majors preparing for the job market. But when he looked at how these highly trained students were actually working, he found a glaring disconnect. Out of 200 seniors, 80% did not have a single AI coding agent installed on their computers. Many were trying to write complex code on outdated versions of Windows. They were taking passive notes and operating with an intense fear of making an error in their syntax. They were behaving exactly how the education system had trained them to behave. After 16 years inside an expensive, highly structured academic pipeline, these students had arrived at the very edge of computer science, completely disconnected from the active tools and problem-solving methods required to actually do the work. This raises a serious question about how we teach. How does a massive, structured educational pipeline end up actively suppressing a student's natural drive to experiment? The answer maps perfectly to an old computing problem in early artificial intelligence. Researchers call it the vanishing gradient. This diagram illustrates how older AI systems, known as recurrent neural networks, or RNNs, used to process data. An RNN is a type of algorithm designed to read information sequentially, moving strictly step by step down a rigid pipeline. The problem with this rigid sequence is mathematical. The algorithm optimizes its learning based on the target at the very end of the line, called the loss function, the mathematical penalty a model receives when its prediction is wrong. But because the early steps in the sequence are so far removed from that final target, the learning signal decays at each node. By the time it reaches the end, the signal is nearly zero. The gradient vanishes. We have built our schools on this exact same architecture. This sequential pipeline was too slow, and the networks were failing to learn. Cho was a postdoctoral researcher at the University of Montreal, working alongside Yoshua Bengio, one of the leading figures in modern AI. They needed a way to bypass the vanishing gradient. The solution came from one of their interns, Dmitry Bogdanow, who conceptualized a completely new mechanism called attention. Attention is a technique that allows an algorithm to weigh the importance of different pieces of input data simultaneously, rather than processing them one by one. This diagram shows how attention destroys the sequential pipeline. Instead of forcing data through every single node, the model creates direct shortcuts. It looks across the entire dataset and links the final goal directly to the specific information that matters most to the translation. The system stopped passively consuming a stream of sequential data. It began actively mining the universe of information for the precise signals it needed to solve the problem in front of it. By choosing what to prioritize, the model functions less like a passive recording and more like a focused researcher. It demonstrates that the key to high-level performance isn't the volume of data processed, it's the ability to filter for what actually matters. Cho's modern research focuses on something called world models, which offers a clear look at how this active filtering mirrors human thought. Imagine you are planning a trip to Paris. You don't sit down and calculate every individual physical footstep it will take to walk from your front door to the airport gate and finally to your seat on the plane. Calculating every single footstep is the equivalent of a computer rendering every single pixel in a video frame. It is an exhausting, rigid sequence of steps. This mirrors how traditional education operates, forcing students to memorize isolated formulas and grammar rules without context. A functional human brain operates in what researchers call a latent space, a high-level conceptual representation of data, stripped of unnecessary background noise. You picture the destination, Paris, and work backward, planning the major milestones rather than the individual footsteps. Our educational pipeline insists that students meticulously calculate every pixel of rote information. It denies them the opportunity to master the latent space, where high-level conceptual problem-solving actually happens. Realizing this flaw in his own classroom, Cho decided to force a system override. He completely abandoned the traditional pixel-by-pixel syllabus. Instead, he required every single one of his 200 computer science students to install AI coding agents and rely on them to handle the granular syntax generation. Cho spends his lectures vibe coding, building complete live web applications in front of the class. Because the AI agent handles the syntax, the class focuses entirely on the high-level architecture and logic. Outsourcing the rote pixels entirely shifts the psychology of the room. The students have a safe boundary where they can build, test, and break their applications without the paralyzing fear of a single missed semicolon failing an entire assignment. This active experimentation is the only way to trigger a step function jump, the kind of sudden, nonlinear growth that breaks the slow, linear scaling laws of traditional study. The rise of AI agents exposed a deep structural failure in the factory model of learning. To survive an automated future, we must stop programming humans like sequential algorithms and start teaching them how to pay attention.